Hello, my name is James Riley Snyder, and I'm a research associate at the Institute of Infrastructure and Environment in the School of Engineering at the University of Edinburgh. I'm also a visiting fellow at the School of History, Classics and Archaeology at Newcastle University. I'm currently on the project Earthen Empire, earth and turf building in the Roman Northwest, where we're analyzing and identifying earth and turf construction materials in the northwestern provinces of the Roman Empire. Now, when we talk about the different types of earthen architecture, today we have four main categories of earthen architecture that are still being applied today. The first is rammed earth, which is essentially a drier mix of earth material, significantly compacted into formwork. The second type we have, which is similar, is cob. In this case, it's applied wetter. It has usually straw or hay fibers mixed in with it, and is applied in handfuls in layers as well, but doesn't typically have the formwork. The most ubiquitous that probably everyone is most familiar with is mud brick. That is something that gets applied quite regularly throughout the world. And then there's stacked turf construction, which is a little less known, but is still applied, especially in Icelandic structures, as well as the Scottish Highlands. Now, this is where the immediate topsoil layer is cut out and then into blocks and then stacked on top of each other. Now, from an archaeological point of view, we have identified all of these, and even within just the Roman period, we have testament to these four different types of materials, as well as kind of blurred lines between some of them. For instance, we have here Punic Roman mud brick walls in Utica. In the middle, we have stacked turf rampart from the Roman fort of Vindolanda near Hadrian's Wall. And we have earth mass walls at Rimini in Italy. Now, I should say that earth mass walls are kind of a general blanket term that can refer to both cob and rammed earth, but also a hybrid of the two, which is shuttered cob, which is a wetter material compacted into a formwork. Now, one of our goals has been to identify these materials and to both excavate and sample them for analytical techniques. In the main examples that we're having from this project, they come from environments where turf were quite important. One of the case studies that we have here was Vindolanda from the previous slide, but we also have the Antonine Wall, which is a linear barrier similar to Hadrian's Wall, but in this case entirely built of turf superstructure. Here we have been able to excavate along one section of the Antonine Wall and extract numerous samples of the turf layers from the wall itself. And from these samples, we've created thin sections and done micromorphology to identify where the turfs generally come from, what environment they come from, how they were applied, what kind of engineering principles. Now, this is the key point. This current project combines engineering and archaeology to look at both the mechanical properties of these materials, but also how they're applied within an archaeological context. One of the things that we've done in terms of the engineering techniques is that we've been able to recreate some of these stacked turf walls and monitor them over a period of time to see how they settle, the moisture content, and then with the ultimate goal to test their compressive strength and in what way they fail. Now, this is something that's extremely important for understanding because there's been absolutely no work on this, yet this material is still used within vernacular construction especially. So it's a combination of understanding both the historical importance but also its kind of modern implications for construction, especially sustainability, if this were to be more widespread, encouraged for more widespread construction. But one of the things that I wanted to talk more specifically today about was earth mass construction walls in Roman Britain. Now, I can't give you any specific details on the provenance of these samples that I'll be talking about because they've yet to be published, but I do want to talk about the importance of the different styles of analysis that we've used, including most recently microCT scanning, which has opened the doors quite a bit on our understanding of how these materials have been created and applied. Now, obviously, the first step is to understand the micromorphology. So again, we sampled these materials, we were able to get thin sections, and then qualitatively analyze them through microscopy. In this way, we were able to identify what were the raw components of this composite material. What things were they intentionally adding in? What things got added in on accident? How they were distributed throughout the matrix? And essentially just understand the human impact of the materials that we're looking at. In addition to that, similarly to the turf that I showed you earlier, we wanted to look at the mechanical characteristics, the mechanical properties of these materials. Luckily, we were able to get just enough material to be able to do some compressive and flexure testing of actual archaeological materials. Now, this has been a very interesting and rewarding process as we've been able to cut up and examine this material for preparation of samples. But in addition, we've also seen that the comparison between the mechanical properties, especially the compressive strength and flexure strength, is that they do fall within the spectrum of modern construction in earth mass walling. So somewhere between modern rammed earth and modern cob construction. So what we've generally found through the micromorphology is that this material is actually shuttered cob. So it's a wetter mix of material that's added into a formwork and compacted to a degree in order to get a homogeneous structure. Now, what we were able to do is introduce microCT scanning. One of the reasons that we were doing this in the first place was to identify how this material reacted before and after it had been mechanically tested. So we did scans of 3 samples prior to being tested for compressive strength, and then scanned them afterwards to see how they failed or where they failed. Specifically on the microstructure, how did they fail? This is something that goes beyond the traditional micromorphological approach, where we can understand the layering, the human impact, to see how the material itself reacts to certain mechanical stresses. But what we didn't realize is just how far this how far this CT scanning went to complementing micromorphological examination. One of the things that we've seen is that through the identification of the microscopic points of failure, we've been able to visualize this quite clearly through CT scanning, which again helps us identify how the individual raw materials themselves, the component materials, are influencing how the material reacts mechanically. We're also able to use the CT scanning to actually quantify. So a lot of quantifying quantitative analysis of the proportions of aggregate materials, the pore structure, things like that. What we didn't expect is to find just how thoroughly mixed in this seemingly organic fibrous reinforcement material was not was identified in micromorphology, but wasn't identified in the complex structure that was seen in the CT scanning. So what we've been able to say is, now that we're going back to recreate this material for further engineering testing, for further mechanical testing, we now know that we actually have to add in a specific proportion of fibrous material to equate what we're seeing from the archaeological evidence. So then what we've seen is that microCT scanning has actually provided us the foundations for the recreation of this material. Not only the recreation for engineering purposes, but for characterizing how the people chose the types of materials that they were going to mix in for their shuttered cog construction. It's still early days in our application of microCT scanning within the Earthen Empire project, but we feel that it has a great potential to give us a lot to discuss in terms of both the materials and the potential for visualizations. Thank you very much for your time, and I look forward to discussing this with you further.